Hey y'all, welcome to Miss Clark's chemistry class. This lesson is about titrations. I also have a lab where you can do a titration. But if you don't even know what a titration is, this is where you need to start. A titration is a lab procedure. It's something that you can do. It is where you can figure out an unknown concentration of an acid or a base by adding a known concentration of the acid or base. It depends whichever one you're doing. And you would utilize the neutralization reaction, where you add acid to base and you get salt and water. They're going to neutralize. So you can add a known concentration of acid or base to an unknown concentration of acid or base until you get it into neutral. Then you can calculate the unknown's molarity. Get some notes, get something to write with, and let's get started. Okay, so first let's remember about that neutralization reaction. A neutralization reaction, that is a double replacement reaction. If you remember way back to when we talked about double replacement reactions, we said that a good reaction would either form a solid precipitate. That was kind of what we were focusing on when we talked about double replacement reactions. But we also said if a double replacement reaction forms water, that was a good reaction. And we also said if we get a gas. This is normally taught in AP chemistry, and we are talking about general and honors chemistry. Okay, so we can see that this neutralization reaction is a good double replacement reaction. Let's look at an example. If we had for our acid, let's say we had hydrobromic acid, and if we had for our base, lithium hydroxide. The salt we would form, now remember, salt is just a generic name for an ionic compound, and this is just a double replacement. So we're going to put our lithium, that's going to be our cation, with bromine, that's going to be our anion. And since both of these are ones, remember lithium is a +1, bromine is a -1. When they come together, they're going to come together in a 1-to-1 ratio, lithium bromide. And then when H and OH come together, we get water. Now, I really enjoy writing water HOH. I feel when you write HOH, number one, it makes it easier to balance. It is still H2O. There's still two H's and one O. But I also feel it helps us to remember that water is amphoteric, meaning it can act as an acid. It's starting with an H, but it ends with an OH, just like a base. It can act like an acid or a base. I just find that handy. Normally we would need to balance this, but it is already balanced. This is going to be the reaction that we use to figure out our unknown acid or base. So titrations. If you're trying to figure out the concentration of the base, you're going to use an acid that you know the concentration of. Vice versa. If you're trying to figure out the concentration of the acid, you're going to need to use a known concentration of base. So one is added to the other, the acid to the base to the acid, until the amount of moles of acid and base are equal. That's our neutralization reaction, y'all. This is called the equivalence point, when the moles of H pluses and the moles of OH minuses are equal. This is really important. This is the point we're trying to get to, because this is when we can calculate and solve for our unknown. In my lab, we're going to start with a known concentration of acid. So this hydrochloric acid here, let's just say that it is 2.3 molar, let's just say. And we're going to dispense using a burette. Now, burettes are a piece of glassware, a piece of lab equipment that is used to dispense very controlled amounts. So we're going to use this burette and we're going to dispense, let's say, 10 milliliters of acid. Okay, so after we've added our 10 milliliters of acid, we need to add an indicator. We're going to use phenolphthalein. So we're going to add a few drops. It's going to be in a dropper bottle. We're going to add this to our flask. Now, I realize I've kind of got this acid is drawn like a blue color. That's just so you can see it. It's going to be clear. And when you add this phenolphthalein in, it is also going to be clear because phenolphthalein only indicates for a base. Now, phenolphthalein can indicate right when a solution starts to turn basic. That's why we're going to use phenolphthalein and not a different indicator. So we've added our phenolphthalein in. Now it is time to start adding our base. So now that we've got our phenolphthalein, now we're ready to start adding our base. So we're going to drop some base in, and we're going to keep dropping base in, but you want to do this very slowly because the very moment that the base hits the bottom and you get a spot of pink, that means we're getting close. Slow down your burettes where you're only dropping in a drop, one drop at a time. And after each drop, you're swirling. Now we are looking for the faintest pink. Now after you swirl, a lot of times this pink's going to go away and you just keep getting the clear. Again, it's going to drop and get the pink and you're going to swirl and it's going to go away. If you're adding in the base dropwise, swirling after every turn, eventually your flask is going to get this pale tinge of a pink. Maybe I shouldn't have used a black background. Maybe I should have used a white background. I'm sorry. Pale pink. Stop. You're there. Because remember, we're wanting to neutralize the solution. But unfortunately, I don't have an indicator that's going to tell me when I'm neutral. I only have an indicator that tells me right past neutral, right slightly basic. Now, when we get to this pink color here, this is called the end point. The end point is when you get the color change. That's how you know stop adding the base. This end point means we're right past the equivalence point. Remember, the equivalence point is at neutral. That's where we're trying to get. But again, don't have an indicator. So we want just on the other side of the equivalence point, which is the end point, which is when you're going to get that pale pink. Now, if you're not going dropwise, or if you think, oh, that pale pink isn't really that pale, let me go ahead and add one more drop. Oftentimes you'll get something that's like this. As pretty as it is, it's way too basic. We've gone way too far. If that's the case, if we go too far and our beaker looks like this, again, it is pretty. We're going to have to go back over here, add some more acid, turn it back clear, and then add more base, and hopefully this time try to get to our end point, the very pale pink. These are the basic procedures of a titration. If we were to graph our results, let's see what that would look like. If you have a known acid and you're trying to figure out the base like we were just doing, this is going to be the graph because we're starting at a very low pH because it's acid. We're going to add base, add base, add base. Right here at pH 7 and where that crosses our graph, this is the equivalence point. And when we stop, we probably stop just right above the equivalence point, and that's going to be the end point. When you have a strong acid or a strong base, you get this real big stretched out graph. It rises real sharp with that big pH change, and then it starts to level out. Here is if we started with the base. If we knew most of the information about our base, the molarity and the volume, we would start at a high pH. And then as we add acid, we get that sharp decline, and then it's going to steady out. Again, same thing. At where the pH is 7, that's going to be the equivalence point. If we were solving for an unknown concentration of acid, we would have an indicator that indicates for acid. So our endpoint's going to be just on the opposite side because we are not going to get a color change until our solution turns slightly acidic. But when the solution is when it's a weak acid or a weak base, we see there's not that sharp incline for that change of pH on both of these graphs. The equivalence points and the endpoints are going to be in the same spot. When we're trying to calculate for our unknown molarity, this is the formula that we're going to use. It looks a lot like the dilution formula for solutions. So if we were going to solve this problem using the information that we just used in my example, we said that the molarity of the acid was 2.3 molar, and we used 10 milliliters of it. Let's just pretend that we used 12 milliliters of base. We need to figure out what the molarity of the base is. So to get X by itself, we're going to divide by 12. Then we need to multiply 2.3 times 10 divided by 12. I'm getting the molarity to be 1.9. Now, to use this formula, your hydrogens and your hydroxides have to be in the same ratio. What I mean by that is let me change colors right quick so you can see what I'm talking about. We used hydrochloric acid, HCl, and we used sodium hydroxide, NaOH. There's one hydrogen for every one hydroxide. You can use this formula when your acid puts out the same amount of hydrogen ions as your base puts out hydroxide ions. It needs to be in a 1-to-1 ratio. So 1-to-1, 2-to-2, 3-to-3. If it doesn't match, like for example, let's say we used sulfuric acid and sodium hydroxide. We're not in balance anymore. We've got 2-to-1. When you have a situation like that, you've got to put a little bit of stoichiometry into the problem. Here, let me show you. In this example, we're going to use phosphoric acid, H3PO4. It's 1.35 molar. We're going to have 20 milliliters of it. And for our unknown base, we're going to use 15 milliliters, and it's going to be calcium hydroxide. So you're going to start with what you know the most about. We know the most about our acid. I'm going to start with the milliliters. You know what? Let me back up. I'm not going to use 20 milliliters. I've got to use liters because we're going to use the molarity formula. Molarity equals moles over liters. So we need liters. So 20 milliliters, we have got the same thing as 0.020 liters. So that's what we're going to start with, 0.020 liters. And that is of my acid, H3PO4. Now, I know that if my molarity is 1.35, then that would be saying I've got 1.35 moles per every 1 liter. So I'm going to put that there. For every 1 liter, because I've got have my liters cancel out, I have 1.35 moles. Do you see how I turned that molarity into moles over liters? I just used 1 liter. And so the moles would have to be the same thing as the molarity. Okay, so my liters are going to cancel out. Now I'm ready for moles. Let me put phosphoric acid back into the problem so you can see what's happening. This is the mole ratio. First time I put mole on bottom, I'm going to put mole on top, and I'm going to change to what I'm trying to find more information about. That's calcium hydroxide. Now that's what I'm trying to figure out. How many moles of calcium hydroxide? So I'm done here. Now I would need to have this balanced chemical equation, and I should have already done that, y'all. H3PO4. I'm reacting that with calcium hydroxide in this neutralization reaction. I'm going to get calcium phosphate. Remember, calcium is a 2, phosphate is a 3, and then you're going to get water. I like HOH because it helps me think. So if I've got 3 H's, 2 hydroxides, I'm going to know that means this is going to be a 6. So that means I'm going to need a 3 here, and I'm going to need a 2 here to make there be 6 hydrogens. Now, when I do that, that gives me 2 phosphates, but that's okay. I've already got 2 phosphates. And when I did that, that gave me 3 calciums, but that's okay. I've got 3 calciums. 6 hydrogens, 6 hydrogens, 6 hydroxides, 6 hydroxides, 3 calciums, 3 calcium, 2 phosphate, done. Now we're ready to do that mole-to-mole ratio. Calcium hydroxide, I've got 3. Phosphoric acid, I've got 2. I'm ready. All of my units cancel. I'm ready to put this into the formula, and this is going to tell me how many moles of calcium hydroxide. So I'm going to put in 0.02 times 1.35 times 3 divided by 2 equals. I am getting 0.0405 moles. I'm trying to find concentration. That's molarity, and I know the volume, 15 milliliters, 0.015 liters. So I'm going to put that into my problem. I've got moles here, moles divided by liters, 0.015 liters, moles over liters. This is going to give me molarity. Divided by 0.015 equals, I am getting my molarity to be 2.7 molar, and that is for my calcium hydroxide. That was a little messy, y'all. I hope you followed. I hope that helped you understand titrations a little bit. I wanted to make sure and give you some definitions, what a titration is, kind of go over what to expect in the lab procedures so you will understand what's happening there. Make sure and show you that math using the MV equals MV formula. Also, make sure you understand you can only use that when your hydrogens and hydroxides are in the same ratio. Also, showing you what to do if they're not in the same ratio. I really hope this lesson helped. Until next time, bye y'all.